Hi students, welcome to Inside Physics. This is Srinivas. Today we will see what is a dipole. Actually, we are dealing with electric fields and charges. That is called electrostatics. The study of charges at rest is called electrostatics. See, now what is a dipole? A dipole is a combination of two opposite and equal charges placed some distance between them. Okay, two point charges placed some distance apart to equal and opposite charges is called a dipole. Now, what happens if a dipole is placed in a uniform electric field? That is what we are going to see in today's class. A dipole in a uniform electric field. Suppose we consider a uniform electric field in this direction. Okay, so the electric lines of force will be parallel to each other in a uniform electric field. If we place a dipole in this electric field, what will be the condition of the dipole and what are the forces acting on the dipole? We will see here. See, consider a dipole placed in this electric field. This is minus, this is positive charge. Okay, a dipole placed at an angle theta making with the direction of electric field is placed in a uniform electric field E bar. Okay, now there will be a force acting on this electric field because we know that a charge placed in an electric field will experience a force of EQ. This is electric field into the charge placed in the electric field. So if this is positive charge, the force experienced will be in this direction. Okay. If this is negative charge, the force of attraction, that means the force experienced by this charge will be in this direction. So in this way, two forces act on these two charges of the dipole in opposite directions. Okay, if this charge is taken as, see, minus QE, and this force acts on this charge is taken as plus QE, so the net force acting on this dipole will be the net force acting on this dipole will be 0. That means the force acting in this direction and this force acting in this direction on this charge. So there is no net charge, and this net charge is 0 means that there is no translatory motion for this dipole. Okay, because the equal and opposite charges are acting in opposite directions and the net force will be 0 on this dipole. So two forces acting at different points of the dipole means there will be a couple acting. Couple means a rotating force, a torque. Couple means a rotating force and also called torque will act on this dipole because these two forces acting at different points of the dipole. Okay, now we see what the dipole will experience a couple. See, this is also we will call represent with tau, and the couple acting on the dipole will be, see, if we take the perpendicular distance of the dipole and that if we consider this as a triangle ABC and the distance between these two charges is 2a, right? If this is AC, the perpendicular distance between these two forces. Now the couple acting will be, we know that either of the forces, right, either of the force into perpendicular distance, either of the force into perpendicular distance. That means we can take either this force or this force, that is equal to eq into perpendicular distance AC. See, we know that AC is nothing but, if we take this as sine theta, the sine theta will be opposite side by hypotenuse. So we can write, see here, sine theta is equal to BC by 2A. So, sorry, AC by 2A. Here AC is equal to 2A sine theta. So this distance, perpendicular distance, will be 2A sine theta according to the property of triangle. So we can write the perpendicular distance as AC, and that is equal to EQ into AC is 2A sine theta. Right. See here, 2A into Q. We know that the dipole moment of a dipole is the distance between the charges and multiplied by the charge, any one of the charge. So this term can be written as the dipole moment P into sine theta, P sine theta. So this is the couple or torque acting on the dipole. Okay, so here this EP and the couple will be acting perpendicular to both electric field and dipole moment. So here we can write the couple acting will be E bar cross P bar. Okay, the couple will be acting perpendicular to both electric field and dipole moment. So in this form, EP sin theta, we can take it as a cross product of electric field and dipole moment. This is the couple acting on the dipole, which causes the dipole to rotate in a uniform electric field. Okay, see, with this couple acting, the dipole may rotate with some angles in the electric field. Now we will see after this the potential due to a dipole placed in a uniform electric field. Okay, see, next thing we will see the potential due to a dipole placed in a uniform electric field. For this we know, we just derived that tau bar is equal to E bar cross P bar. This is the couple acting on the dipole. See, if this couple is acting on the dipole and we are doing some work against this couple or torque, and we are doing a small work to rotate this dipole through a small angle d theta, then the work done can be taken as the small work done to rotate this dipole against this couple with some angle d theta. We know that work done is equal to force into displacement. Here the displacement is not a linear displacement. The displacement is an angular displacement, which we will take in terms of theta. So the force into displacement is work done, we know that. So here the small work done will be EP sin theta d theta. So this is the force I am writing here. E bar cross P bar is EP sin theta d theta. So here this is the small work done in rotating the dipole through a small angle d theta. If we consider the total work done in rotating the dipole between the angles theta 1 and theta 2, if you want to calculate the total work done, why we need to calculate the total work done? The total work done in rotating this dipole is stored as potential energy of the dipole. That is what we want to calculate here. So here the total work done will be taken as, we will integrate this one between the limits theta 1 and theta 2. Why means, we are considering that the dipole will be rotated between theta 1 and theta 2. So that's why we will integrate this one between the limits theta 1 and theta 2. So here EP sin theta d theta. So here work done will be EP, the sin integration of sin theta is minus cos theta between the limits theta 1 and theta 2. Okay, this can be written as EP into cos theta 1 minus cos theta 2. Okay, this is the total work done against this force in rotating the dipole from theta 1 to theta 2. Okay, if we consider initially the dipole is at perpendicular to the electric field, that means initially the dipole is perpendicular to the electric field. In this case, this theta 1 will become 90 degrees. Initially the dipole is at perpendicular to the electric field. Next, and that dipole which is perpendicular to the electric field is rotated through an angle theta. Okay, theta 2 through an angle theta will become theta here. Now the work done can be written as cos theta 1. We know that cos theta 1 is 0. Okay, so cos 90 will become 0, and this cos theta 2 will become cos theta. Okay, so here work done can be written as minus P E cos theta. So by this we can write it as a dot product of P bar and E bar. So here now we have calculated the total work done in moving this dipole between the angles theta 1 and theta 2. Okay, so the formula can be written as minus dot E bar. So here the dipole moment is a vector quantity, electric field is also a vector quantity. This work done will be stored as a potential energy in this dipole. So potential energy, potential. The potential due to this dipole can be written as P bar dot E bar. Okay, so this is how we have seen that the couple acting on a dipole placed in a uniform electric field, and thereby we have calculated the potential due to this dipole placed in this uniform electric field. Okay, this is the potential and couple acting on the dipole. That's all for now, and in the next class we will move to some problems on this dipole, and we will move to capacitance.